Hello friends, today we are guiding you to prepare interview questions on machine learning. In comments you can share the topic of your interest. Our team will prepare the video for you. Before continue to our session, we request you to join our channel for all the latest updates. Our team of technical and subject matter experts are working hard to create valuable content just for you. So please make sure to hit the subscribe button, like and comment on our videos, and click the bell icon to stay updated with our latest videos. What is feature selection, and why is it important? Feature selection is the process of selecting a subset of relevant features, variables or predictors, from the original set of features in a dataset to improve the performance of a machine learning model. It involves eliminating redundant, irrelevant, or noisy features, keeping only the most significant ones that contribute meaningfully to the model's predictive power. There are several methods of feature selection. Filter methods. These involve statistical tests to measure the relevance of each feature independently, for example, correlation, chi-square test. Wrapper methods. These use a specific machine learning model to evaluate feature subsets and select the best combination based on model performance, for example, recursive feature elimination. Embedded methods. These perform feature selection during model training, for example, lasso regression. Decision tree-based methods. Importance of feature selection reduces overfitting. By removing irrelevant or redundant features, feature selection helps to simplify the model, reducing the risk of overfitting. Improves model performance. Fewer features mean less complexity, often leading to faster training times and improved generalization. Enhances interpretability. Focusing on key features makes the model easier to interpret, especially when dealing with high-dimensional datasets. Saves computational resources. Reducing the number of features can speed up model training and prediction, especially in large datasets. In summary, feature selection improves model accuracy, efficiency, and interpretability, making it a critical step in the machine learning pipeline. What is the difference between one-hot encoding and label encoding? One-hot encoding and label encoding are two common techniques used to convert categorical variables into numerical representations for machine learning models. However, they differ in how they encode the categories and how they affect the model. Label encoding. In label encoding, each category is assigned a unique integer label. For example, if you have a color feature with values red, blue, green, label encoding would assign red 0, blue 1, green 2. This method is simple and works well for ordinal data, where the order of the categories matters. However, label encoding can introduce unintended ordinal relationships for nominal data, potentially misleading models into assuming an inherent ranking between categories. One-hot encoding. One-hot encoding creates binary columns for each category. Each category is represented as a vector with a 1 in the column corresponding to the category and 0 in the others. For example, with the color feature, one-hot encoding would create 3 columns, red, blue, and green, where each row is a binary vector indicating the presence of a color. This method avoids creating artificial ordinal relationships but can lead to high-dimensional datasets if there are many unique categories. In summary, one-hot encoding is better for nominal data, while label encoding is suitable for ordinal data. Both techniques help prepare categorical data for machine learning models. What is dimensionality reduction, and why is it important? Dimensionality reduction is the process of reducing the number of input features in a dataset while preserving as much information as possible. This technique is used to simplify models, improve computational efficiency, and reduce the risk of overfitting, especially when dealing with high-dimensional data, many features or variables. The goal is to identify a smaller set of features that can explain most of the variance in the data. Two popular methods of dimensionality reduction are principal component analysis, PCA. PCA is a linear technique that transforms the data into a new coordinate system, where the axes, principal components, correspond to the directions of maximum variance in the data. It reduces dimensions by selecting the most important components and discarding the less informative ones. T-distributed stochastic neighbor embedding, TSNE, TSNE is a nonlinear method used for visualizing high-dimensional data in lower dimensions, usually 2D or 3D. It is particularly useful for exploring the structure of complex data sets. Importance of dimensionality reduction reduces overfitting. By eliminating noise and irrelevant features, dimensionality reduction can help the model generalize better. Improves computational efficiency, reducing the number of features speeds up model training and prediction. Enhanced visualization, for complex data sets, reducing dimensions to 2D or 3D allows for easier interpretation and visualization. In summary, dimensionality reduction is critical for enhancing model performance, interpretability, and efficiency, especially in datasets with many features. How do you handle categorical variables in a dataset? Handling categorical variables is an essential step in the data preprocessing pipeline for machine learning models. Since most machine learning algorithms require numerical input, categorical data must be converted into a numerical format. There are several methods to handle categorical variables. Label encoding. In label encoding, each unique category is assigned an integer value. This method is suitable for ordinal variables, where there is a meaningful order, for example, low, medium, high. However, label encoding may not be appropriate for nominal variables, as it can introduce unintended ordinal relationships. One-hot encoding. One-hot encoding creates a binary column for each category in a categorical variable. Each column represents the presence, 1, or absence, 0, of a specific category. This method avoids introducing any ordinal relationships and is ideal for nominal variables, for example, red, blue, green. However, it can lead to high-dimensional datasets if the categorical variable has many unique categories. Target encoding. Target encoding involves encoding categories based on the mean of the target variable for each category. It's useful for high cardinality categorical features but should be used with caution to avoid overfitting. Binary encoding. Binary encoding combines the benefits of label encoding and one-hot encoding. It is used for high cardinality variables to reduce dimensionality. In summary, the method chosen depends on the nature of the categorical variable and the model being used, with one-hot encoding being the most common for nominal variables. What is the difference between normalization and standardization? Normalization and standardization are two common techniques used to scale numerical data, making it easier for machine learning algorithms to process. Though they both aim to adjust the range or distribution of data, they do so in different ways. Normalization, also known as min-max scaling, normalization transforms the data into a specific range, typically 0, 1. It is calculated by subtracting the minimum value of the feature and then dividing by the range, max, min. Normalized value equals x minus min max minus min backslash text normalized value equals backslash frac x backslash text min backslash text max backslash text min normalized value equals max minus minx minus min. Normalization is useful when the data has a known, bounded range, or when you need the data to fit within a specific range, as required by algorithms like neural networks or k-nearest neighbors. Standardization, or Z-score normalization, transforms the data to have a mean of 0 and a standard deviation of 1. It is calculated as standardized value equals x minus mu sigma backslash text standardized value equals backslash frac x backslash mu backslash sigma standardized value equals sigma x minus mu, where mu backslash mu is the mean and sigma backslash sigma is the standard deviation. Standardization is often preferred when the data is normally distributed or when dealing with algorithms like linear regression or SVM that assume data is centered around 0. In summary, normalization is useful for bounded data and specific algorithms, while standardization is typically preferred when data needs to be modeled with techniques that assume a normal distribution or are sensitive to the scale. Thanks for watching the video till the end. If you liked the video and haven't subscribed yet, please hit subscribe button, like and comment on our videos, and click the bell icon to stay updated with our latest videos. In comments you can share the topic of your interest. Our team will prepare the video for you.